Previously we saw that the electric field at a particular point due to an electric dipole in an axial line. Now we are going to take the case where we want to find out the electric field at a particular point P in an equatorial line. So in this case, I have a minus q out here, a plus q charge out here, separated by a distance of 2a. I take this midpoint between these two charges, where the distance from the midpoint to minus q is a and 2 plus q is a. Hence it becomes 2a. And I take a point P, somewhere out here I take a point P at a distance x from the midpoint, and I name this point as P. This is the point where I have to find the electric field due to this dipole. Now as we know that the electric field due to Q, since it is a positive charge, so the direction of the electric field will be away from it. Hence E2 is the electric field due to this plus Q charge. And then minus Q, since it is a negative charge, therefore the direction of the electric field in case of negative charge will be towards it. So E1 is the electric field due to minus Q, E2 is the electric field due to plus Q, separated by a distance of 2a. And our aim is to find the electric field at point P and also to find out the direction of the electric field. E1 is the electric field due to minus Q, E2 is the electric field due to plus Q. So the equation for E1 is 1 divided by 4 pi epsilon naught Q divided by R square. R square in this case is going to be AP, which is this distance from minus Q to point P is my R square. So in order to find this distance from A to P, I use the Pythagoras theorem, which comes out to be root over x square plus a square. And same will be the case for BP. It is also going to be x square plus a square. And I got this distance using the Pythagoras theorem. Hence I replace AP square as x square plus a square. Root will be cancelled out since this is a square. Same will be the case in case of electric field E2, which was being produced by plus Q charge, which is 1 by 4 pi epsilon naught Q divided by BP square. This distance from B to P. The expression for E2 becomes 1 divided by 4 pi epsilon naught Q divided by BP square. So on substituting for BP square, it becomes 1 divided by 4 pi epsilon naught Q divided by x square plus a square. So out here you see that E1 is equal to E2. So E1 out here is equal to E2. So I can take this E1 and E2 as E. So I found the expression for E1 and E2. And now my aim is to find the resultant electric field at point P due to this E1 and E2. So in order to find out the resultant electric field, since electric field is a vector quantity, so in this case we are going to make use of the vector addition rule. So out here you see that this electric field, I can take this electric field as the resultant electric field since E1 and E2 are equal. Therefore I can take this as a resultant electric field. Now what I do is I am going to take a parallel line, a line parallel to this line. Okay, and then this is theta, this is also theta. So I can take this as theta and also this as theta. Okay, if this is theta, this is theta. With respect to this, I can take this as theta, and since this angle will be equal to this angle, therefore this can also be theta. Now I'm going to resolve this electric field component into two parts. One is on this direction, which is E sine theta, and one on this direction, also E sine theta, and then another on this direction. This will be E cos theta, and there will be one more component which is going to act on this direction, on the same direction, and this is also going to be E cos of angle theta. So out here in this diagram you see that I have E sin theta and E sin theta acting on opposite direction, whereas E cos theta are on the same direction. Therefore, what we do is E sin theta being opposite cancel out each other. We can cancel out E sin theta and consider E cos theta. Since it is on the same side, hence they add up. Therefore, your resultant electric field becomes ER is equal to twice of E cos of angle theta. So, ER becomes 2 into 1 by 4 pi epsilon naught Q divided by x square plus A square. I am just substituting out here for this electric field. Since E1 and E2 are equal, since E1 is equal to E2, therefore I can take it as E, okay, and then I substitute it for A. And now what I am left with is this cos of angle theta. Now we use that particular term. Some people have curly brown hair based by hypotenuse. So what I do is I can take any of this, either this or this, either this part or this part. So this side was x square plus A square, okay, to the power half, which is whole thing under root. This side was A, this side was x, and we got this by using the Pythagoras theorem. So I substitute for cos of angle theta, hence I get the equation to be ER is equal to 2 into 1 by 4 pi epsilon naught AQ divided by x square plus A square 3 by 2. And then since I know the electric dipole moment P is equal to twice AQ, therefore what I do is I take this 2, I take this A and Q, I substitute for twice AQ as P in this equation, and then the resultant electric field that I get is this particular equation. So this is the equation for my resultant electric field due to this dipole at this particular point P. Also, for short dipole, that is A very less than x, means this distance is so small, they are very close to each other. This distance are so small, almost like a point. Then I can neglect A and I just take this distance as x. I can only consider x neglecting A. Therefore, the equation becomes 1 divided by 4 pi epsilon naught P divided by x cube. You see there is a similarity between the electric field at axial line and also the electric field at equatorial line, which is resultant electric field is inversely proportional to 1 divided by x cube, even in the case of equatorial line. The direction of the electric field is opposite to P. This is the direction of P, whereas the direction of the electric field is on this side. Also, the direction of the electric field in case of equatorial line is opposite to that of P. The electric field is on this direction, whereas the direction of P is on this direction. Also, one thing, that the direction of the electric field at any point in the equatorial line, suppose if I take this point instead of this, then also the direction of the electric field will always be opposite to the direction of P. So we have got an equation for the electric field in the case of equatorial line and also in the case of axial line. And now we want to make a comparison between the electric field equation we got in case of equatorial as well as axial line. So in the case of equatorial line, we got 1 by 4 pi epsilon naught P divided by x cube. Whereas in the case of axial line, it was 1 divided by 4 pi epsilon naught twice P divided by x cube. This is the case of axial line, and this is the case of equatorial line. So out here you see that this is a single P. Okay, this is 1P, whereas this is 2P. So this means that the strength of the electric field in case of the electric field at the axial point is double the strength than in comparison to the equatorial point. The strength of the electric field in case of axial line, is double. It is double than in comparison to the equatorial line. So this is one of the comparison that is usually asked in the examination. And then what we do is we again compare the electric field by a point charge and also the electric field by a dipole. Now in case of point charge, the electric field is given by Q divided by x square, and in case of dipole it is given as E is equal to P divided by x to the power cube. So out here you see that this case is the one where the denominator is a little less than in this case. Here it is square. So the denominator in this case, in the case of point charges, is a little less compared to the denominator in the case of dipole, which means that the electric field in the case of point charges are going to be a little higher than in the case of dipole with respect to the distance. Hence we can conclude that in the case of a point charge, the electric field is going to deplete a little lesser than in the case of dipole. In the case of dipole, the electric field is going to deplete faster because here the denominator is more. So denominator more means the numerator is decreasing, and hence the electric field is going to decrease. Hence at a particular distance, the electric field due to the dipole is going to deplete faster, whereas the electric field due to a point charge is going to deplete a little slower in comparison to the dipole. And also in comparison between these two, the axial has double the strength than compared to the electric field at the axial point is double the strength in comparison to the equatorial point.